Hi, this is lecture 1.5 of the first week of the SAGE-based course on Monte Carlo Methods. This is Raz again, your lecturer. In this video, we'll focus on sets. We will be learning some elementary set theory. Sets are perhaps the most fundamental concepts in mathematics. What is a set? Set is nothing but a collection of distinct elements. We write a set by enclosing its elements within curly brackets. Let us see some examples of this next. The collection of star and a circle is denoted by star comma circle inside the curly braces. Left curly brace and the right curly brace, like that. We can name the set by the letter A, for example, and write A equals star comma circle. Now the question, is the set star, star, and a circle a set? So you should know that this won't be a set because it is not a collection of distinct elements, unless we have a way of distinguishing between the first star and the second star. A set of numbers and letters that I like is the set BD6PQ9. The set of the first Greek alphabets is the set containing alpha, beta, gamma, delta, and epsilon. The set that contains no elements is the empty set, and it is denoted by a big 0 with a slash over it. That's the special symbol for the empty set, and the empty set is nothing but a collection of nothing, which is denoted by a left curly brace followed by a right curly brace. We say an element belongs to or does not belong to a set with these two binary operators. This is the symbol for belongs to, and when you have a slash through it, it's the symbol for does not belong to. For example, the star belongs to the set containing the star and a circle, but the element X inside a circled cross does not belong to the set containing a star and a circle. Another example is that B belongs to the set containing B, D, 6, P, Q, and 9, but 8 does not belong to that set. The question, is 9 an element of the set containing 3, 4, 1, 5, 2, 8, 6, 7? Clearly it isn't. We say a set C is a subset of a set D and write C subset D. So this C-like symbol is called the subset symbol. If every element of C is also an element of D, we say C is a subset of D. That's the definition of a subset. So for instance, the set containing the star is a subset of the set containing the star and the circle. Question, is the set containing 6 and 9 a subset of the set containing BD6PQ9? And the answer is, of course, yes, because every element of the set containing 6 and 9, namely 6 and 9, is also an element of the larger set. Set operations. We can add distinct new elements to an existing set by the union operation, denoted by this big U symbol. For example, the set open circle and filled circle union with the set containing the star is nothing but the set containing the open circle, the filled circle, and star. So if I ask you what is the union of the set containing the empty circle and the filled circle with the set containing the filled circle, the answer should be clearly the set containing the filled circle and the empty circle, namely the first set. Therefore, when you add an element that is already in a set, you get the same set back. More formally, we write the union of two sets A and B as follows. A union B is the set of all x such that x is an element of A or x is an element of B. So the symbols above are read just like I did, and this colon is there to be thought of as such that. Similarly, the intersection of two sets A and B, written as A intersection B. So now you see the intersection symbol is like a big N. A intersect B is simply the set of all x such that x belongs to A and x belongs to B. So A intersection B just means that it is the set of elements that belong to both A and B. For example, the open circle and the closed circle set intersected with the set containing the open circle is simply the set containing the open circle. Again, the set containing the open circle and the closed circle intersected with the set containing the closed circle is simply the set containing the closed circle. Finally, when you take the intersection of two sets and there is nothing in common between those two sets, we get the empty set as its intersection. In this instance, these two sets are said to be disjoint. The set difference of two sets A and B is written as A set minus B, this sort of backward slash symbol. It is the set of all x such that x is an element of A and x is not an element of B. So A minus B, or A set minus B, is the set of elements that belong to A and not belong to B. For example, the set containing the open circle and the closed circle minus the set containing the open circle is simply the set containing the closed circle, because this is the only element that is in the first set but also not in the second set. The equality of two sets A and B is defined in terms of subsets as follows. We say a set A equals to a set B if and only if A is a subset of B and B is a subset of A. As I already said, two sets A and B are said to be disjoint if their intersection is the empty set. Finally, given a universal set capital Omega, this is the capital Omega symbol, we define the complement of a subset A of the universal set by A complement. We put a little c superscripting A. So A complement is simply the set minus of the A from the universal set. That is, it's the set of all x such that x is in the universal set and x is not in A. Here is an interactive Venn diagram just to illustrate some of these concepts. This is grabbed from Interact at the miscellaneous page of Sage Wiki. Suppose x is 1, 2, 3 and A, y is 2, A, 3, 4 and apple, and z is A, B, 10 and apple. Then x intersection with y is 2, 3, A, x intersection with z is A, x, y intersection with z is A and apple, and the intersection of all three sets is simply A. And that's what you see in this Venn diagram for the three sets x, y, and z, or z. So we can go and change this to add, say, an orange to y and hit Shift Enter, and now you have the set Z, the set Y, which is in blue, has an orange, and all the other sets are as they are. Okay, so before we proceed any further with making sets in Sage, I suggest that you go back and review all this material. It's quite a lot of notation thrown at you. Just remember that these are the most elementary operations that we need to really get under our belt, and the rest of the course simply will use these concepts to help us articulate what we want to actually say and what we actually mean when we do computational statistical experiments.